Yeah, good afternoon and welcome to this talk. As a quick introduction, a few words about our company and what we do. We, since 25 years, we provide intelligent and automated test solutions to the automotive industry, focusing on unit testing, on integration testing. We have a global presence with locations in the US, in Japan, and also here in Shanghai. And as part of this little introduction, we thought it would also be fun to share a little bit our personal background and our long-term relationship with AUTOSAR. So maybe on my side, I've started 20 years ago from a tool vendor perspective. So I started in 2007 working for DSpace, providing support training consultings on a lot of topics about AUTOSAR, including AUTOSAR architecture. So really in the early days of the AUTOSAR 2 version. And yeah, almost at the same time, Nabile was also an early adopter of the AUTOSAR standard.
Yes, indeed. So my first connection with AUTOSAR was in 2010, and I had this OEM perspective because I was working for Peugeot Citroën in France, developing powertrain software following AUTOSAR and ISO 26262 processes. So yeah, I think we have at least a lot of experience to talk about this topic today, because nowadays there's a lot of new challenges we see in this AUTOSAR software development.
Yeah, and today we want to talk about unified toolchain strategies and why is this needed? We see a strong trend for harmonizing toolchains, simplifying tool landscapes in the automotive world. And this actually comes from two perspectives. So one dimension for toolchain harmonization is across teams and departments, and the second dimension is across development methods. And let's just take a minute to look a little bit deeper into what this means. So on the teams and departments level, we see that historically in automotive, many companies, they have independent tools, methods, and processes for the different domains. And in a world where every domain had a specific ECU, that was something that maybe made sense. But now in the SDV area, we heard a lot of talks today and yesterday about how AUTOSAR is also contributing to more zonal architectures where on the same hardware, different features from different domains are running. This really means that it becomes more and more impractical if different teams are working in different tool chains. So if different developers from different domains contribute to the same ECU, they should work with the same process. They should share the same CI pipelines, etc. for faster iterations. The second dimension is the development methods. And if we look a little bit how the history looks for that context, back in the 90s, people were writing assembler, right? And that was a language which was very close to the machine, very close to the computer, but not so close to the human brain. So then people said, okay, software is becoming more complex. We need a language which is easier to use. And then they started using abstract languages like C code, and they needed translation from a tool like a compiler. But the complexity didn't stop growing. And then again, around 20 years ago, people said, we need another language which is closer to the human brain, further away from the machine, more suitable for the engineers that have the domain knowledge, and they probably want to implement their algorithms without thinking about things like data types and memory mapping and so on. And then the model-based development paradigm was invented, with the de facto standard being Simulink and Stateflow today. And then again, similar to the compiler, there's the code generator, which is able to produce code out of it. And this is, of course, the de facto standard today in most companies. But we also see, obviously, that some features are still handwritten code because from the way the algorithm is designed, it's not that suitable for model-based. So pretty much they both coexist, but also in the future, the model-based world will make sense for certain algorithms which have more control engineering state and which will be developed by engineers that don't want to dive into the code. So that means we have different quadrants, 4 quadrants, which we need to look at when we want to come up with an efficient testing strategy. So for the model-based, we have, of course, Simulink. Then we have code generators like Embedded Coder and Target Link. And in this world, we already have, looking from the AUTOSAR perspective, 2 different areas, we have the classic AutoSAR, where we have a pretty mature tooling. We have an automatic RTE stubbing, so for testing the models and the code, this is pretty matured and proven in use. For the AutoSAR adaptive, the world is not 100% mature. The stubbing is not fully ready. So this is something which is currently in progress. But then we have the 4 other quadrants. We have for the handwritten code, the typical tool of choice is Visual Studio Code for many teams. And there we have other challenges. We often have to do some manual stubbing. We have to take care about the build configurations. For the AutoSAR adaptive, we have additional challenges like no standardized approach for mocking services for the management of threads, etc., etc. So we have these 4 different worlds in which we want to test, and they all have a lot of things in common. In all the 4 worlds, we need stubbing and mocking for the parts which are missing. We need requirements traceability, which can be to tools like Polarion, Codebeamer, DOORS, etc., or maybe Excel in some projects. We need to look at structural coverage. We need to look at runtime errors. We need a CI/CD integration, and of course, we need a tool qualification to put the confidence into the tool, especially for applications that have a safety critical nature and maybe even a certain ASIL level from ISO 26262. And all these challenges down there, they are pretty similar for these 4 quadrants, and we think that it's not very practical to solve them 4 times. And this is where Nabile will take over to talk more about the unified concept for testing all the 4 quadrants.
Yeah, thank you, Markus. So yeah, how do we help realize the this unified testing strategy? And we basically start by looking at it from the perspective of the tester. So what do the tester need when it is about to test the different software unit types? And the goal is, of course, to focus on the test activity itself. So basically writing a test specification and a test implementation which focuses on the functionality of the software unit, which means the tester has to basically deal with the stimuli of the software unit and the expected behavior. And in order to achieve that, the user should not have to handle the harnessing, the stub generation, and so on. All this stuff needs to be automated. And thanks to the AutoSAR standardized interfaces, this is something we can rely on to automate this work. And we have to address this basically for the different quadrants. So on the model-based side, we have classic and adaptive. And in there, we basically need automating stubbing and mockings, which enable mill and seal testing. And this also comes with some challenges that the test harness should enable the test cases to talk to the model and to the code at the same time, which means we need a reliable mapping between the model and the code. On the C code, on the hand code, on the pure code side, on the classic side, of course, the RTE stub, but this is pretty well standardized. And on the adaptive side, we need to come up with concepts for stubbing the service interfaces, and in order to isolate ourselves from the network bindings. And next to this, of course, the unified testing strategy needs to cover the other requirements of automotive grade testing, which basically means dealing with requirement traceability, where we need to integrate with requirement management tool where we can import requirements, connect to our trace with our test cases and our software unit, be able to update requirement in case of requirement changes, but also in order to be able to push test results to this environment. And also this unified test strategy needs to be covered with the different testing methods, ranging from functional testing through things like equivalence classes, boundary value analysis, and so on, all the way to formal methods. And since we always all deal with safety critical application, tool qualification is an important aspect. And with this approach, we can solve this tool qualification once, and all these quadrants can benefit from this. And last but not least, especially in the SDV area, CI/CD is super important. And with this strategy, we can implement our CI pipeline, so then the same APIs and interfaces can be used for the different levels. So more concretely, with some example how the mocks works. So basically, we need to deal with mocks on the model level, but also on the code level. And on the model level, I mean, when you have things like sender receiver, things are pretty simple because you just basically harness the model with input and output ports. But as soon as you have client servers, you need to provide mock implementation for the servers. If your component is a server, you need to provide a client. If your component is a client, you need to provide a mock server. And this is something we can automate. Yeah, we can automate during the project creation. But on top of that, we can also provide a scheduler because we can deal with software components with multiple runnables. We have to execute them. We don't have in this environment the real OS and the task mapping and so on. So we have to simulate that. And for adaptive is almost always necessary because we deal with service-oriented architecture, and the system is always exposing service interfaces which we have to mock. So basically under the BTC block, you have the software component or the adaptive application, and this is fully handled. On the code level, we already mentioned RTE stub, 3D standardized. So we got ourselves from the real RTE in order to test on host PC on the level of the unit, and on the adaptive level, we need to come up with a concept which can help us decouple from the network binding, because for most of application, when you have adaptive software component, testing this on the code level usually means connecting maybe to some IP layer, compiling on Linux, etc. You basically cannot do this very easily on the x86 or 64 platforms, and coming up with a concept where the interface, the service interface, including it to simple variable for testing, is very helpful. And next to that, of course, for the tester, we need to provide an abstract language which helps to basically focus on the interfaces without really caring about their real implementation. So we just talk about signal names, right? And it can be offered as a graphical interface where we abstract, again, you just see basically signal test steps, input, output signals. There is a pendant in the code where you basically have this implementation. So whether you test seal only, you can use that, or when you test model based, you can also use the other one where the mill and seal execution are just one click button away. And last but not least, there's also one more thing, because it's not only about stubbing interfaces, because we also need to deal with scheduler, because again, we don't have the real operating system, and for unit testing and integration testing also can be considered, like with the level 1 integration, where we have basically the whole application software and some services from the basic software. We come up with so this is not very clear, but basically with an abstract scheduler generation where you can define init tasks, asynchronous tasks, periodic tasks, and whether you have runnable in classic or method in adaptive, you can basically use this to define the orchestration of the integration that you want to test. It can address units or integration level, and this can run on x86 and 64 platform. And I would like to conclude with the CI pipeline, because in the SDV area, what I would say only matters is the CI pipeline at the end of the day, because you need a process which shows you the quality gate to be prepared for your over-the-air updates. And when we look at the fork right now, basically you can rely on the same CI APIs to define a pipeline for your different unit types. And this includes creating the test project for classic adaptive MBD handcode. Whenever you have model, you will go through mill simulation or back-to-back testing. Code coverage analysis is common to all of them. Robustness checks like division by zero, downcast, boundary value analysis, and so on. And of course, you can this is the process and release. And
talk a little bit about the role we think AI will play in this particular use cases. And we want to start by bringing a little bit of structure into the discussion, because AI means different things to different people, and in the automotive software engineering process, it can be used for different things. And we want to structure that a little bit to make it also clear that these are different use cases. And the use case number one, where we bring AI into the into the test process, is AI as a co-pilot. So this is really something where the engineer stays in the driver's seat. The engineer will be in charge of the process, but he will have a little AI companion helping him get some things done faster. Like you have in Copilot, maybe in Microsoft Outlook, that helps you write the email faster. You also have the Copilot in the test environment that helps you write the test case faster. So this is the Copilot use case where it helps you in your daily work. The second role that the AI can play in our engineering process is being a process automator. We could also call this agentic AI. And this is something where an AI agent will autonomously walk through different steps of your process. And since the AI alone cannot do all the work, because it cannot be trusted, it's not reproducible, it cannot be audited, the AI needs help. The AI needs help from trusted and certified tools. And there is a way to call these tools, which is an API called MCP. And this is something the tools should provide so that the AI agent can walk us through the engineering process fully autonomously and call the different tools. Use case number 3 is AI as a code generator. So, of course, different AI tools are also good in producing code. And then the question is, what do we do with this code? How can we trust it? Does the AI generate the code in the right way? So we need to discuss how to test this. And then, of course, number 4 is when AI goes in the vehicle, and especially from an engineering perspective, this is not that much talking about large language models. I mean, large language models could play a role in the vehicle for things like voice assistant, but then often the LLM is running in the cloud. So here we are more talking about the traditional machine learning kind of AI, which goes into the vehicle and which then, of course, also should be tested. So these are the 4 levels of AI adoption we wanted to discuss, and we want to focus a little bit on the AI as a code generator, because we talked about these 4 quadrants of different environments where we have different verification challenges: classic and adaptive, model-based and hand code. And actually, we have to make 6 out of these 4 now, because the AI-generated code, either for classic or for adaptive, is also something where we need a strategy. So we have basically 6 different use cases for which we hope to come up with a unified test and verification strategy. And especially when it comes to AI-generated code, we have many customer meetings, and most of these meetings lead to 3 questions, which we are discussing. Question number 1 is, can AI become good enough that we trust the code it writes? Right? So AI, the models are getting better every day. So maybe the models one day will be so good that we can just trust them. And here the clear answer is there's no demonstrable path to a model being so reliable that its output can be used for safety critical systems, because no matter how good the AI is, again, it's a reasoning mechanism. It's not predictable, it's not reproducible, it's not explainable. So we cannot rely on the AI to always do the right thing. The second question which comes up, okay, then the AI can maybe check its own output. Maybe it can generate some test cases and review itself. But this leads to the same problem. We don't have the clear KPIs that show us if and when the testing is complete. And then the third question is, maybe we use like the virtual 4i principle, and we use a second AI. So maybe we use Anthropic to generate the code, and we use OpenAI to test it, and then they are sort of independent. But even this independence does not create the trust that we need. It, again, doesn't have the explainability. It cannot be audited. It doesn't have an end criteria. So what do we do? The good news is, and I think we have 2 good news. Good news number 1, we never had trusted code in automotive. We never trusted the code. If the code was handwritten, we didn't trust it. If the code was auto-generated from Simulink, we didn't trust it. And we have great standard and great methods that allow us to bring trust into this code. ISO 26262 is a good example, which talks us through the different steps, through the different use cases we should apply to trust the code. So we can apply all these on the AI-generated code. The problem is when we generate code with the AI, we also do it because we hope to do to be faster, and then some of these test methods, they are relatively time-consuming. But one of the most powerful methods for verification is something called formal verification, which is, there are different core technologies which can perform automated mathematical proof that a certain software can never violate a safety requirement. The big problem for applying these highly automated verification methods, they need good requirements, because if you don't have good requirements, this level of automation cannot be achieved. And to be honest, in the past 20 years, the requirements quality in many automotive projects was not that good. Someone to blame here is probably also Simulink, because in a model-based world, obviously the Simulink is often seen as like an executable specification, and if I do model-based design, maybe it's quite natural that I'm not too motivated to write good requirements. So we've seen projects where the requirements document was an auto-generated PDF with Simulink screenshots, and this might have worked, but we believe that in the future, in the use cases where people want to generate code with AI, the requirements quality will dramatically improve. It has to, because it's the only input we can give to the AI to generate code. So if the requirements are bad or incomplete, then the whole development process will not work. And if the AI forces requirements quality up, and this means it opens up the whole new world for automated verification that was not there before. Verification and testing was time-consuming and needed a lot of manual work because the requirements were not written down. The requirements, and I said there were no requirements, but that's not true. The requirements were there. They were just hidden in the brain of the engineer who created the model, and this brain then also had to do the testing and verification. But when AI forces requirement quality to go up, it opens up a whole new world for having a dramatically higher degree of automation in the whole verification process. So the way we see this is, in a step one, we would create some good requirements, some good specifications. We will then use the AI of our choice to generate the code. We will then apply all the automated and ISO 26262 certified verification steps on this generated code. And then either everything is green and we have trusted code, or we find a problem, which could be a requirement being violated, which could be a structural problem like a division by zero. It could be a boundary value that is violated. And one thing the AI-generated code has in common with the code generated from a Simulink model, in both cases, I do not want to touch the code. I do not want to manually change the code, because then I would cut myself from future improvements. So we should have a loop back into the specification step to report this violation so that the AI can start again and create a new version of the code where this problem is fixed. And we already talked about agentic workflows. So this whole cycle can be like a self-improving, self-healing AI agent where the verification step is automated, and then the verification step sends the information about the violation actually back into the process, and then this third thing can turn in a loop until everything is green. Okay, so maybe back to Nabile for some key takeaways and a short summary.
Yeah, so basically today we have identified basically the need of coming up with a unified strategy for testing AUTOSAR classic and adaptive software components, either generated from model-based, written by hand code, or generated by AI. And the goal of this is to be able to eliminate the fragmentation which used to be there, especially in the classic area where different tools could fulfill this. But nowadays in the SDV area, as we have seen, Most of these components also we have seen in many talks that classic and adaptive, they can stay inside the same ECU. And here we basically have the chance to consolidate the traceability, rely on one-time tool qualification, and also unified CI/CD pipelines. Secondly, we have seen that with this unified approach, we can address safety and compliance, which means on the first hand, the test strategy will enable all the verification techniques from requirement-based testing all the way to formal verification, but also addressing the specificities of the model-based software development, like the back-to-back testing, comparing model and code, and all this under a unified tool which is qualified for, certified for ISO 26262. And last but not least, Markus, AI in the game. Oh, sorry, that's one last point. We talked about AI, which basically can help improve the speed of our software development, also relying on this unified platform. But here we also need to consider that AI-generated code is untrusted code by definition, and we need to combine this with verification techniques. We don't have to reinvent new ones, but just apply the ones which are already proven in use, and they can run pretty well on the AI-generated code, which we just consider typically as a handwritten code. And yeah, so this was our talk today, and basically all the things we discussed, they are not only concept, they also exist concretely, and we provide this test strategies for model, hand code, and AI, C and C++, classic and adaptive. The solution is integrated in Simulink, so you don't have to leave your IDE, but as well as in VS Code, where the whole stubbing, the test creation, the traceability with the requirements, and all the reporting can be handled from the same platform. So yeah, so it was Markus and me.
Yeah, so please connect with us. We also have a WeChat that you can get in touch with. We have a booth outside, so the short time that is left on the conference, please also stop by if you have any further questions. And if you're based in China, we also have Min here from our BTC China team, and you can keep in touch with her as well. So yeah, thank you. And if there are any questions.
Thank you. Thank you for the great presentation and for addressing the problem of AI-generated code. I saw a demo, and I wanted to get your opinion about this. I saw a demo at CES where AWS is using Khoury to generate code, which is based on AI, but to ensure that it meets compliance with ISO and functional safety, they are using agentic AI to create a framework of testing. So I wanted to, I don't know if you saw it and this implementation, but I wanted to get your opinion of using AI to test AI.
Yeah, I was at CES, and of course the Khoury agent from AWS is a great product. I don't know how accessible it is here in China, but definitely the AI is also in the Khoury world more playing the role of the orchestrator of the process. So the actual final answer for ISO compliance, it needs to come from underlying formal methods, which tools like we produce. So the AI agent need to call these kind of underlying technologies, yeah, of course. My understanding is that AWS does not provide directly these technologies, so they will just provide the agent, which then will rely on probably a specialized tool which may have maybe some domain-specific capabilities, and then this can be easily integrated. So the Khoury has the ability to include MCP servers, and if the different domain-specific specialized tools provide these MCP capabilities, then it's just a plug and play to add them in this process.
Is it that easy, indeed? Does it really work to use the agentic framework and the orchestration to actually get functional safety code?
It is surprisingly easy, yes, because the way to explain the AI, how to call these certified and trusted tools, is basically just skill plus MCP, and the skill is just text. So it's really like a recipe in a cookbook, and you tell the AI, do this and this and this, and then the AI will run through it, and hopefully it will do it. But if it doesn't do it, then in the end, something will be missing, because the actual evidence lies in the reports that are produced by the trusted tools. And if all these reports are there and the AI didn't miss anything, then we can claim completeness. And if the AI forgot to call a tool, so okay, maybe you want to have code coverage in your process and the AI, for some stupid reason, forgot to call this process step, okay, then the report is missing and you know that something is missing. So it's relatively easy to show completeness in this process based on the reports coming from the ground truth tools, if you want.
Any more questions? All right, then thank you very much.
Thank you very much.